It's my pleasure to introduce Dr. MacKie. Dr. MacKie is an assistant professor at University of Florida. She got her PhD at Stanford University, working with Dr. Dustin Schroeder and the Stanford Radioglaciology group there. Her research covers a wide range of topics, including geophysical glaciology, machine learning and geostatics methods, and glacial geology. And today she will talk about integrating geologic realism into subglacial investigation. So with that, let's welcome Dr. MacKie.
Awesome. Thank you for that introduction, and thank you for having me here. It's really exciting to be here as a geophysical glaciologist because so much of the work I do and the data that I work with has its origins from this department. My PhD advisor came through here. Many of my collaborators have come through UTIG, so I'm excited to be here. So today I'm going to talk about what I mean by geological realism and why it's important for studying the subglacial environment and how we can better incorporate this into our understanding of ice sheets. A lot of the work I'll share today has been done by my students. I've got 3 PhD students, Michelle, Michael, and Nia, and a small army of undergrads who have done an outstanding job at producing actual research. So for those of you who haven't visited, the University of Florida is located in North Central Florida at one of the highest peaks in Florida. But the rest of Florida is much closer to sea level and dangerously close to being below sea level. I'm often asked what I'm doing in Florida studying glaciers. And the honest answer is I've got a nice job there. But what I tell people is that Florida has more to lose than any other state when it comes to sea level rise. And it's really important that us in southern states are focused on this issue. This is an IPCC figure showing future sea level rise projections. And there's a lot of uncertainty going forward over the next century. And I just want to highlight this dashed high impact, low likelihood storyline that accounts for ice sheet instabilities. So the potential for ice sheet processes to unfold that could lead to the catastrophic loss of our ice sheet mass. And it's incredibly important, especially in states like Florida, that we are able to rigorously investigate these possibilities and adapt to those trajectories if needed. A big part of modeling ice sheet behavior and understanding what controls ice sheet movement is the subglacial environment. And that includes the topography, the hydrology, and the geology beneath the ice. Those things are, of course, incredibly difficult to resolve at large scales and high resolutions that are needed to incorporate this into ice sheet models. We have a lot of geophysical data available to us to investigate this environment, including a lot of data collected by members of this department. We have ice penetrating radar, seismics, gravity and magnetics, and a whole other slew of geophysical observations. And we know both from theoretical models and experimental work, including a lot of work done by Don and Ginny and other members of this department, that these basal conditions have a huge impact on modeled ice sheet behavior. And it's incredibly important to resolve what these conditions are. One of the things that we use ice penetrating radar for is to measure the bed elevation and ice thickness. So this figure is showing the coverage of radar data in Antarctica. And that information is used to construct these continuous models of the bed topography that are used in virtually every ice sheet investigation. So the bed topography has a huge impact on how ice flows and how sensitive our ice sheets are to warming climate and oceans. But you'll notice that there are a lot of gaps in these observations. This gap has recently been filled in, but you can see that in these interpolations, these gaps are very smoothed because we have places where there are tens or even hundreds of kilometers where we don't have measurements. And in our interpolations, that shows up as places in the bed topography where the slope of the bed is effectively 0 for hundreds of kilometers. And while Florida is actually that flat, I'd bet that East Antarctica, which is situated on a large craton, is much more rugged. So we're missing information by not accounting for this realistic roughness information in our representations of the bed. So how do we actually initialize our ice sheet models if we don't have a complete understanding of the basal conditions? Well, what we do, or the ingredients we need for an ice sheet model are some governing physics or sliding law, which we still don't really know. There's a lot of debate over which sliding laws we should use, which ones are correct in certain locations. I don't have strong opinions about it, but there are a lot of different hypotheses for how the governing physics should work. We also need topography. We need some information on our ice rheology. And then we also use a basal friction coefficient parameter, which is intended to loosely describe a lot of the geological conditions at the base of the ice sheet. So to get there, we start with some smooth topography. We pick a sliding law. Then we use those things to do an inversion for what our ice rheology should be, and then use all of that to do an inversion for the basal friction coefficient. And there are some variations on this process as well, but generally speaking, we're using the ice sheet model physics itself to determine the parameters that go into that ice sheet model. So we've got this kind of house of cards logic where we're inverting for all of our parameters that then go into our ice sheet model in order to test how our ice sheet model responds to those parameters in sea level rise. And this is kind of a problem because, one, we shouldn't really be using our model to determine our model parameters. Also, it doesn't give us a good way at verifying our physics. And there's also a lot of circular reasoning going into this, and it makes it really difficult to untangle this process. The other thing is that there's really not geological information going into this. We're not using all of this, wealth of geological knowledge that many people in this department have acquired. I also just want to show this figure. This is a biplot. I don't know if people look at biplots anymore, but what it is the first principal component against the second principal component, and each of these vectors is a different variable. I've plotted different bed variables in Antarctica, including an estimate of the friction coefficient, the bed topography elevation, the topography variation or roughness, modeled bed temperature, and then someone did a machine learning analysis to map the likelihood of having sedimentary basins across Antarctica. So I plotted all of these things against each other, and variables that are correlated in a biplot are approximately parallel, and variables that are uncorrelated are orthogonal to each other. And what we're seeing is the friction coefficient has some correlation with the bed elevation, but is actually almost entirely uncorrelated to the bed roughness, the temperature, our estimates of what the bed geology is and all that. So what that's saying is that the friction coefficient is actually not related to what we think we know about the geological conditions at the bed. So I really don't think that this friction coefficient is a meaningful representation of the geology. That, or we just have our estimates of temperature and roughness and sedimentary basins wrong, or some combination of this. But I just want to underscore this point that currently ice sheet models and many of our investigations of ice sheet processes lack geological realism. We're not accurately accounting for the roughness information or geological knowledge when we are studying this environment. And a big goal of my research is to figure out how we can bring more of this geological realism into our understanding of the subglacial environment so that we can better understand how it influences ice sheet behavior and sea level rise downstream. So a big part of my research is geostatistical simulation, and I just want to highlight this study by John Goff, who is the first person to do this on an ice sheet. And the idea of geostatistical simulation is that you randomly simulate some geological phenomenon so that it is statistically realistic. So this figure is showing measured bed elevation at Thwaites Glacier from ice penetrating radar, and a geostatistical interpolation of this data, showing the realistic looking topography. And that is like a big component of my research. So the idea behind geostatistical simulation is, let's say we're looking at some cross-section of topography under the ice, and we have these blue dots that represent measurements of bed elevation. And we want to interpolate that. If you wanted to do a deterministic interpolation, it would look something like this red line. So this red line is optimized for accuracy. This is the most accurate possible interpolation of those measurements. And that gives us something like this, like a Kriging interpolation. So say we have some real topography, we pulled out measurements, we do a Kriging interpolation. This is the most accurate possible way to do this interpolation, but it is incredibly smooth. It does not reproduce the variability of measurements, and it really doesn't look anything like our actual topography. But this is what we're relying on for ice sheet investigations. Alternatively, we can generate multiple stochastic realizations or geostatistical simulations that reproduce the variability of our measurements and sample the parameter space. So the advantage of this simulation approach is that we can generate multiple realizations to quantify our uncertainty. And you could imagine applying an ice sheet model to each one of those. And that way you're quantifying your uncertainty in your ice sheet model behavior with respect to the topographic uncertainty, which at the end of the day is the thing we really want. And then this thing also looks much more realistic. So this kind of thinking is used a lot in groundwater hydrology and in oil exploration, because those guys figured out early on that the subsurface heterogeneity and variability is incredibly important for governing the larger scale behavior of that system. So in this talk, I'm going to talk a lot about how we can use geostatistical simulations coupled with additional geophysical observations to improve our understanding of the subglacial processes, including the hydrology and basal sliding, and down the line, ultimately strengthen our ability to quantify uncertainty in ice sheet behavior. So one of the important things that we can use this geostatistically simulated topography for is for mapping the subglacial hydrology. Much like rivers on land, the subglacial channels under the ice are routed by the bed topography. This is a figure by Winnie Chu showing meltwater in Greenland and how these meltwater pulses are associated with speedups in ice velocity. So understanding where this water is traveling underneath the ice is very important for understanding how it influences ice sheet movement. This is a picture I took on the surface of Greenland in 2019, which was a really big melt year. This is the top of a moulin. So I'm sorry there's nothing for scale, but this is a massive amount of water that's being delivered right to the base of the ice. And that, of course, has an impact on how the ice sheet is moving, and it reduces the friction at the bed. This is another picture I took from that summer, or this is me lifting up my tent. Because this was such a big melt year, we had to move our tents every few days because the surface was just melting around us, and every day the ceiling of your tent would get closer and closer to your face. So you'd have to kind of shimmy in. So this is what it would look like after about 4 days. So I know this isn't like a super precise metric, but I think we can say that there's about 3 inches of surface melt happening each day. So that's a huge amount of water reaching the base of the ice. But without, perfect knowledge of the topography, it's hard to say where that water is going. So we can use geostatistical simulation to help us out there. I demonstrated this for Jakobshavn Glacier in Greenland. Here are some radar measurements, and I generated geostatistical simulations of what that topography could look like, and then applied a simple water routing model to each of them. And this is the existing kind of state-of-the-art bed machine map of the bed topography, which is a lot smoother. And these are the channels for some of these different realizations and for this previous estimate. And you can see that the modeled flow paths differ across these realizations. Some of the main features are the same, but there are places where our channels are located in different places. So this allows us to visualize our uncertainty in where the water is flowing underneath the ice. And this plot shows the mean of 250 hydrological realizations. I don't know why I inverted the color bar, but these light areas are places where we have high confidence in where the water is flowing, and these blurred areas are places where we have lower confidence in whether or not there's a flow path there. And maybe these are places where the channels are also potentially subject to rerouting or water piracy. One of my students is taking this a bit further. They're interested in using more sophisticated hydrological models than what I've used here to see how the topographic roughness and uncertainty affects the distribution of channelized versus distributed flow under the ice. So, stay tuned for more on that. The other really important thing that geostatistical simulation and topographic roughness allows us to do is investigate basal sliding behaviors. So this was a really small, like 5-kilometer area where we simulated the topography at very high resolution and modeled the ice sheet sliding over this surface. And to do the simulation, I actually used the Geostats Pi software developed by Michael Perch at UT. So, and this is the comparison smooth topography that people use in ice sheet investigations. And what we find is that with a smooth bed, the ice sheet has kind of a plug flow behavior. So it's pretty cool down to the bed and it's moving as a block. But with the rougher topography, it generates a lot more internal deformation and deformation heating. And this leads to the development of a temperate layer or layer of temperate ice at the base of the ice sheet that's rheologically weaker than the top. And we actually took borehole measurements in this area that confirms that there is a thick and highly variable temperate layer at the base of the ice sheet here. So by using realistically rough topography, we are more accurately able to capture fundamental sliding processes. So hopefully I've convinced you that we need more geostatistics in glaciology. But I quickly ran into kind of an issue with limitations in existing geostatistics tools out here. So like I said earlier, I was using the UT, I think it's more of an educational software, but I quickly realized that it's not going to be able to scale to something like this. So geostatistics has historically been used for point data sources like boreholes and well logs, and is almost exclusively used in the oil and mining industries. But our types of problems are very different. We have extremely large data sets, up to tens of millions or hundreds of millions of values that span really large areas. Our data is often gathered along lines. So we have very finely sampled data along track, and then areas with really sparse measurements. And this makes it really hard for a lot of the existing tools to simulate topography at large scales. So I was finding that when I tried to load my data into existing tools, they would just crash, either because the data was too big or because there were numerical instabilities. And then also because geostatistical simulation has historically been used for industry purposes, a lot of these packages are very expensive. They're not designed to be interoperable with a lot of our workflows. And I realized that I wasn't going to be able to do the science I wanted with tools that already existed. So I ended up making my own Python package called GStatSim, which is designed to tackle a lot of these issues. It's open source and all that. This figure shows an example data set of radar bed elevations in Greenland and a bunch of different ways to geostatistically interpolate that data. And I'll just walk you briefly through some of the ways we can do that. So say we have some data and we want to interpolate this. There are a lot of different ways to do geostatistical simulation, but everything I'm going to talk about in this talk is based on the variogram. And the variogram is a measure of spatial covariance in your data. So if you have two measurements that are close together, those are going to be more spatially correlated. They have a lower variance. Measurements that are further apart have a higher variance. And this variogram curve is showing this increase in variance as a function of the separation distance between pairs of points. So measurements that are further apart have more variance, measurements close together, less variance. And we can use this variance to constrain our interpolations. And in sequential Gaussian simulation, the goal is that the simulated topography or whatever reproduces the spatial statistics described by the variogram. So we can use that to do kriging if we want to optimize accuracy. So these are simple kriging and ordinary kriging, different types of kriging, standard deviation or uncertainty for that. But one of the problems with kriging is that it's a lot smoother. So this is the variogram for that input data, and this is the variogram for the kriging interpolation, showing that there's a lot of missing roughness. If we want to add that roughness back, then we use sequential Gaussian simulation, which treats the topography as a random process governed by this covariance information. So how sequential Gaussian works is that, say you have some unknown topography with some measurements. What you do is you randomly select a grid cell you want to simulate, use your variogram and your kriging functions to estimate some mean and variance at that location. So you have some probability distribution over what your elevation is. And then you can randomly sample from that distribution to get your simulated value. And then that becomes part of your conditioning data. And you repeat that process over and over until every grid cell is populated. We can also incorporate anisotropy or preferential smoothness in one direction into both our kriging and sequential Gaussian interpolations. We can account for large-scale trends. We can also even account for differences in the variogram across a location. So the roughness in your topography might change across the region. And so here I've demonstrated we arbitrarily broke this domain up into 3 clusters and assigned a different variogram to each cluster. And you can see that there's some subtle differences in the roughness along those bounds. So there are probably more geologically informed ways to decide what these boundaries are, but basically we can account for non-stationarity in our geostatistical simulations. And that could be really important for certain applications. We can even account for secondary constraints. So this is a map of the ice surface, which has a positive correlation with the bed elevation in many places. And we can impose that correlation onto our simulation or our kriging estimate. So there are ways to account for secondary constraints in geostatistics as well. And finally, we have a lot of different covariance functions that can be used to model different types of spatial phenomenon. And I should mention that this software isn't just for bed topography, it's for anything with a coordinate. Since releasing this last year, this package has had thousands of downloads. It's been used in coursework around the world, and it's being used for all sorts of different geoscientific problems. If none of this made any sense, you can look at our educational Jupyter book, which walks you through some of the theory and the usage for this software package. So hopefully everyone can go and use geostatistics now. One of the main limitations of our software is that it's embarrassingly slow. And that's because of the sequential nature of many geostatistical simulation algorithms. So you have to simulate every single point one at a time. And the computational time grows exponentially with the size of the thing you're simulating and the number of points you have. So it can get pretty unwieldy. And we did a back of the envelope calculation for what it would take to simulate Greenland at like a 200-meter resolution. And it would take about a year to generate one realization. So that's not so good. We don't want that. But fortunately, we can actually parallelize many of the operations that go into determining this probability distribution before we simulate a single value. And I can talk about that in more detail if you're curious about how the math works. But basically, all of the large covariance matrix inversions that go into doing simulations can be parallelized all at once for every single grid cell. And that makes this algorithm actually incredibly parallelizable. So I had an undergrad who published a first author paper on this approach, showing that we can actually bring down the computational time by a lot by parallelizing this across different processors. This is for Pine Island Glacier. So I'm actually feeling very optimistic about being able to scale this up to ice sheet scales. We're also flirting with adapting this to GPUs, which can do lots of these large covariance matrix operations in parallel. So it should be pretty easy to scale this up. Many people in the geostatistics community have been trying to use deep learning to improve the speed of geostatistical simulations, mostly with generative adversarial networks or GANs. And this is kind of a new and exciting research direction, but one of the issues that people have run into with GANs is that, yes, they can generate very believable looking simulations that convince you at the naked eye, but when you actually start to investigate the statistics of those realizations, they don't hold up. They don't pass our math test. And what I mean specifically is that they can undersample the variance in places. They aren't conditioned exactly to existing measurements. So they can fool you a little bit. And we wanted to investigate this problem and see if we can come up with a better way to use deep learning to do geostatistical simulation. And I'll mention that all of this was done by my undergrads. So what you're seeing here is we generated an ensemble of realizations using the traditional sequential Gaussian simulation approach. And this is the mean and the variance. So this is like kind of the truth of what that should look like. And then we trained a GAN and then something called the diffusion neural network to see if it could do the same thing as that and reproduce this behavior. So diffusion neural network is a kind of neural network that uses like a diffusion-like training process to learn the probability space of your training data in order to reproduce that behavior in its generated outputs. So it behaves a little bit differently than a GAN. And the advantage of that is that it's able to honor the statistical information of your inputs with much greater fidelity. So this is the mean and standard deviations of the ensembles generated by these neural networks. And they're both doing all right, but the diffusion network is doing a little bit better at exactly matching observations. We can see that by the zero variance along these flight lines. And this is showing the variograms for a few of those output realizations. So these are kind of the truth variograms or the variograms from the sequential Gaussian simulation realizations. And these are for the diffusion neural network and the GAN. And the GAN is a little all over the place. It's doing an okay, but not amazing job at reproducing the spatial statistics of our geostatistical simulations. But the diffusion network is doing a really nice job. So I think this is kind of an exciting new direction for us. We're thinking about how we can incorporate physics, how we can extrapolate this to other areas. I think this also has implications for large-scale climate modeling, where it can often be really difficult to store these massive ensembles of realizations. But using diffusion neural network approaches, we can better store that information in a latent space and then pull out those realizations when we need them. So we've addressed a lot of the computational aspects and software problems of geostatistical simulation. But those of you who study ice sheets are probably thinking, what about mass conservation constraints on topography? And And these places in pink are areas of fast-flowing ice on our ice sheets, where the principles of mass conservation are used to constrain what the topography should look like under the ice. And the idea is that as ice is flowing, ice mass shouldn't be created or destroyed. So the topography has to be shaped in such a way that allows for that to happen. And without mass conserving topography, our ice sheet models are just going to break and spit out garbage. So having topography that conserves mass is really important for being able to use it in an ice sheet model. So how do we geostatistically simulate topography that also satisfies this physical property? Well, we can do that in a Markov Chain Monte Carlo type way. So Monte Carlo means random sampling, and a Markov chain is a memoryless sequence of decisions or events. And when you put that together, what you get is iterative random perturbations that are done in optimized fashion that allow you to sample the parameter space and get closer to your solution. So what's going on is, you can generate some geostatistical simulation of a phenomenon, calculate some geophysical forward model, erase a little bit of it, resimulate it, recompute your forward model, and see if it improves the fit. And this is a form of Bayesian inference. So it's a really good way to quantify your uncertainty. It's very robust. It's super useful for highly nonlinear inverse problems because you don't have to solve the inverse model explicitly. You just have to calculate the forward model a bunch of times. I think this example is for like modeling porosity or permeability for oil exploration. So this kind of thing has been done before in other fields. And Markov Chain Monte Carlo has been around forever. I don't really think it's seen its full potential because the advantage of or disadvantage of MCMC is that you have to do so many thousands of iterations so it can get computationally inefficient real fast. But now we're starting to reach the point where that's not such a problem anymore. So how it looks like in our world is we generate some geostatistical simulation of topography, compute our forward model, perturb that simulation, recompute the forward model, and then accept or reject those changes depending on these results. So if the new topography, if the new forward model has a lower loss, then we accept this perturbation. If it makes it a worse fit, then we're more likely to reject it, but there's also a non-zero chance that we will accept that perturbation. So we have a little bit of exploration in our sampling. And then we continue doing that over and over again until we reach some convergence threshold. So this is what it looks like for mass conservation. This is Denman Glacier in East Antarctica, and this is Denman Trough, the deepest point on land that is not the seafloor. And this bed actually doesn't show up in the radar because the radar is bouncing off the sides of this canyon, but the mass conservation inversion, this is a previous result, state-of-the-art for Antarctica, shows that we have to have this deep trough here to satisfy conservation of mass constraints. If we just do geostatistical simulation without that, we can't see the trough. But if we combine geostatistical simulation with mass conservation in a Markov Chain Monte Carlo framework, then we get both, which is great. So now we have the ability to incorporate geostatistical simulation into an ice sheet model while satisfying this conservation of mass property. And this is work that's been done by my PhD student, Nia Shao, who's presenting at EGU next week. And she's planning on extending this into an ice sheet model application, seeing how this affects our understanding of the basal friction coefficient and all of that. So I think this is a huge step forward in our ability to incorporate geological realism into ice sheet models. My student, Michael Field, is doing something very similar with gravity inversions. So this is Thwaites Glacier, and this is the Thwaites ice shelf in West Antarctica, this is an incredibly critical place for understanding the stability of the Antarctic ice sheet. Because radar can't see through water and ships aren't getting up in here, it's pretty difficult to constrain what the bathymetry underneath this ice shelf looks like. And that's it's really important that we do, because the bathymetry underneath the ice shelf affects how the ocean circulates underneath here and erodes at the grounding line. And so to estimate what this bathymetry looks like, people rely on gravity inversions. This is airborne gravity data over the ice shelf. So these are the anomalies. And we can use that information to do gravity inversions. Many people have done that before. This is a very challenging inverse problem because it's highly underdetermined. People often solve it in 2D along each flight line and then try and line them up together. But it's tough because there's both unknowns in the density and the topography, and the signal that you're seeing at any given location could come from off-track information as well. So this makes it really difficult because the mass distribution of the Earth is, it depends on a lot of different unknowns. But we can get at that a lot more rigorously within a Markov Chain Monte Carlo framework. So this is the same thing, but for an ice shelf, you can see this is the sub-ice shelf topography, where we are iteratively solving for the bathymetry. My main concern when we got started on this was computational time, because we're running tens of thousands of forward models here and doing tens of thousands of geostatistical simulations. But we actually got it down to about 2 minutes for 10,000 iterations on a laptop. So I think we are done with the days of Markov Chain Monte Carlo being computationally intractable. And Michael found that, well, this is his, the mean of his ensemble of the MCMC topography and the standard deviation. This is the outline of the ice shelf. And this is the difference from the previous estimate in this region, so the previous gravity inversion estimate. So we're seeing differences of upwards of hundreds of meters from previous gravity estimates. And we only have uncertainties of up to about 200 meters. The biggest differences are over in this area. We think this point is a lot deeper than previous estimates. And this has major implications for modeled ocean behavior and grounding line behavior in this region. We also looked at the effect of uncertainties in the density of the material in these inversions. And Michael actually found that while, yes, density does contribute to uncertainty, that effect pales in comparison to uncertainties in how you estimate the regional gravity effect from crustal properties. That was kind of interesting. But anyways, he has an invited talk at EGU next week. So if you're at EGU, be sure to check that out. Okay, so one issue that I've been kind of dancing around is the fact that our radar data isn't always exactly correct. We get a lot of noise from off-track clutter, so that the topography we're measuring isn't necessarily the nadir reflection. And that can lead to hundreds of meters of uncertainties or errors at crossover points. So how do we deal with that in this geostatistics world? And this is just a figure where I used a clutter simulator to simulate what the clutter would look like on some deglaciated topography. And we are seeing multi-100 meter magnitude differences from the truth topography. So that's a big problem. But I think we can actually deal with this in a similar Markov Chain Monte Carlo framework, where we are iteratively simulating the topography and the radar data until we get some ensemble of topographies that honor our clutter information. And this is a problem that my student Michael is going to tackle for the second chapter of his PhD. This is also something that I think has planetary implications. So this figure is from a proposal that I submitted with Gregor Steinberger at JPL, who I think was a postdoc in this department. Another point for UT Austin. But the problem here is, we want to make a better map of the surface topography on Mars. This is showing the state of the art, which was derived from orbital laser measurements. But there's also radar data on Mars as well. So this is showing the relative cover of laser and radar data. And we are interested in using the radar clutter information to better constrain interpolations of the laser altimetry data. So this is a very rough first pass at this, where on each iteration, I perturbed the topography a little bit, recomputed some loss metric based on clutter simulations, and then accept or reject that, etc. I only did 500 iterations because this is still quite slow, but you can kind of see the lines in there where we have the altimetry data in places where we're starting to perturb the bed a few meters, and it gives you a better fit with the radar data. So fingers crossed for that one, but I think there's a lot of other applications where we could use this school of thought. Okay, in the last couple minutes, I'm gonna just talk about potential seismic application. And I wasn't sure if I should share this, but I figured that if there are any weak points in this plan, you will find them. So I am not a seismologist. I'm very grateful that my collaborators on this are. But the last few years, I've been fortunate enough to be part of a joint kind of research and educational program in Svalbard, where we take a group of graduate students out onto this glacier and do active source seismic and radar surveys in order to interpret the subglacial conditions. This is Slakbrain. It's a small glacier. This is only a few kilometers long. It's kind of interesting because it's in a sedimentary basin, and there's this big kind of meltwater pool at the toe of the glacier, and someone sampled this water and found methane in it. So there's probably some kind of interesting connected groundwater subglacial hydrological system. But anyways, this is, thanks to us now, a very well studied and constrained glacier. And there's a potential to do something interesting to figure out more about subglacial geological properties. So, this is some of the shooting we were doing. There's a coal mine in Svalbard that gave us 5 tons of expired dynamite. That for some reason is okay for us to use. But, seems to be working. So we did about, I think 120 of these shots this season. So I just got back a couple weeks ago. One of my students is still up there, I think. But we're doing very long offsets. So, we have geophones laid out across a few kilometers. But we have, multiple different offsets in this data. And we actually found that this generates very strong surface waves. I think I could even feel like a Rayleigh wave on a couple of these shots. So I think there's like a lot we could do this data. And in glaciology, most of the seismic data or seismic analysis we do is just normal incidence reflection information, calculate the acoustic impedance. That's as far as we go. But I think there's more that we can get out of this. I didn't have, one more, sorry. Having a blast. I didn't have a good segue into this slide, but I felt that it was important to mention that last year, Tom Cruise was out there. This is my student in the back who apparently tried to explain geophysics to him. But yeah, so that was exciting, probably the highlight of my career. But anyways, so he was out there filming Mission Impossible 8. But speaking of Mission Impossible, my goal with this ultimately is to be able to do full waveform inversion So this here is not a full waveform inversion. I've only figured out how to model P waves. But like, let's say that we have some simple velocity model, ice sheet, some bed, and we have a shot gather. That's all I know how to do so far. We could really easily set up an MCMC problem to automatically solve for the velocity of this layer using this. Nothing revolutionary here. But I think we could build on this, account for a lot of variability in the velocity, maybe even look at the density, incorporate other waves, maybe even add some like actual rock physics modeling here, and be able to use that on our data from Svalbard and start to develop this full waveform inversion workflow. I think there are going to be a lot of challenges to this. Like one, it's very difficult to model seismic wave propagation through semi-frozen materials. Definitely going to be leaning on my seismology collaborators for this. But this is what I'm hoping to be able to do. And I think this is going to bring us a long ways towards better understanding the geology beneath our ice sheets. So I won't be able to answer any questions about this, but I have many for you all. As a recap, using geostatistics and by combining it with other geophysical information and developing these new open source materials and high performance computing versions of this, we can better utilize our geophysical information and inject more geological realism into our understanding of the subglacial environment. And that has all sorts of implications for our ability to understand the hydrology, the sliding processes, model ice sheets, and quantify uncertainty. Yeah, just to summarize, still much more to do. But I think we have a really clear path for being able to think of our subglacial environment more like this and less like a basal friction coefficient. So thank you. With that, I'll take any questions.
Who's first?
Oh, there.
Hi, really cool talk. I was kind of wondering how different like data resolution inputs impact your models and how you reconcile maybe a really high spatially resolution input data versus one that's right next to it that's maybe really low resolution.
Yeah, that's a good question. Right now, most of our simulations are at a low enough resolution where all our radar data is kind of below that resolution. But once we get down to like 25-meter resolution simulation, which is the finest I've done, then you're really kind of at the mercy of how you all picked your radar bed data and digitize that and everything, and you are prone to artifacts. So there's not like one straight answer for how to deal with that. In the geostatistics community, there are a lot of different things you can do. We can also have our data ungridded when it goes into that interpolation, but it does have a little bit of an effect on how you interpret your variogram and your uncertainty measurements. Yeah.
Well, thanks.
Do a follow-up on that. So can you quantify the uncertainty of the bed from the overlapping uncertainties from the radar versus your geostatistics?
Yeah, so that's
Way that helps, I guess.
Yeah, so that's something that we're for sure thinking about. The challenge is that the crossover errors can vary wildly, sometimes hundreds of meters, sometimes not that much. So I think there's a lot of like non-stationarity in the uncertainty. It has a lot to do with the roughness of the topography. I think it's going to be hard to do it like systematically by just looking at the crossover error uncertainties. So I think ultimately doing like a Markov Chain Monte Carlo clutter simulation thing is going to be a better way to go. But yeah, it does, that is historically what people have used to kind of, they take the crossover errors and take the average and say that's our uncertainty. I don't think that's a good way to do it because you have crossover errors bigger than that. But yeah, that that is what people do.
As a geologist, this is way out of my field, but I wonder what would happen if you went to a recently glaciated terrain like Labrador, say,
Mhm.
and took a limited amount of data, as if you'd just been flying radar over it when it was still covered by ice.
Yeah.
And tested against reality what your results come out to be.
Yeah. I mean, this is you know, I've done a little bit of this to test our oh gosh. So we've done a little bit of that just to test some of the geostatistical simulations. So this is deglaciated topography, and this is just kind of a sanity check. I think there's a lot more we could do with that. Like if we know something about the geology here, we could do like actual, you know, radar clutter simulations. Actually, this is deglaciated topography too. But I think we could potentially find ways to use the geological information from deglaciated terrains and the roughness and all of that, and try and find a link to learn more about that under the ice.
Thank you.
Thank you. Great stuff. So in terms of non-stationary behavior, what are the prospects for both provincing a landscape based on the different variograms, or is there any way to do basically a continuum where you have continual variation in the variogram?
So this is actually my plan for this summer. I do have like a little method for quantifying roughness across an area by doing like a moving window variogram analysis. And my hope is to basically assign like a different variogram parameter for every single grid cell, so that we can do like a fully non-stationary simulation where every time we simulate a point, we just look up the variogram parameters at that grid cell. Yeah, be hard. And there's a little bit of smoothing that comes from that, but yes, that is the goal.